slide. My name is Ed Carroll. I'm a research analyst from Sandia National Laboratory. I had the distinct honor of pulling together a group of people to participate in a IFSR, International Federation of Systems Research, conversation. A conversation is a week-long session. Never mind. Week-long session. Broke my train of thought. So a conversation is a week-long session just on digging into the ideas and principles and things that you came together to read about. Just like any of these sessions here, wouldn't it be nice if you could just spend a week digging into all the things and the new ideas that that session brings up? Well, that's what we did. I picked a team of folks personally. It was by invitation only, who have just significant experience in various different aspects. For example, I have background in software engineering, systems engineering, data analytics. Nancy Hayden has a background in autonomous systems. Sharon Troth has a background in systems engineering. She's what I would call our consummate practitioner. And Dana Grisham has a background in data management, data strategy. Chris Schreiber has a background in managing systems engineering transitions. Bill Schindel has a background in everything, including pattern, model patterns, and well, I can't think of the whole list, it's too long. But he has a significant background, smallest model and model space. Frank Salvatore has pulled together the taxonomy for the Department of Defense and represented the interest of that agency. Elliot Rich is an academic with a background in systems dynamics. Steve Jenkins is what I would consider the consummate ontologist in systems engineering. And Ann O'Neill has a fantastic background in system engineering transformation for major corporations. We didn't intend to go to create a manifesto as the outset of this session. What we intended was to spend a week digging into data-based systems engineering. Not database, but data-based. We, being typical system engineers, particularly old guys and women, we kind of tended to grouse a bit. And so we covered all the topics of all the barriers for why we don't have transition to model-based systems engineering. And then we talked about some positive things of where we could go if we could have that. So I'll tell you a couple things about this before we start out. So to begin with the title, Model-Based Engineering Manifesto, as opposed to Model-Based Systems Engineering Manifesto, we use the term MBE as in a collective sense to represent all the types of model-based engineering, not just systems engineering. We all happen to be systems engineers, but we also think that this is applicable to any kind of model-based engineering platform or practice. The other thing I'll point out is the fine print. We value items on the right, but do not sacrifice the items on the left. So what we mean by that is that obviously the things on the right, your right, are all valuable things. Yes, we know we have artifacts. We need to have artifacts. We're never going to get rid of artifacts, even if we're totally digital environment, at least for a long time. But the point here is that a model contains much more information than an artifact does. And so we value that information collection more than we value the output of the artifacts themselves. Independence comes out of where we've been for a long time. We spent the last 15 years trying to get people to build models, and independent models happens to be where most people went. We applaud their ability to, or their interest in building models, but what we really want to get to is integrated models. So you can imagine a the digital twin. If you haven't seen a video on what the digital twin might look like someday, do a Google search and find it. It's a pretty astounding vision of where we might want to go in our entire system development industry. But there's some underlying themes of that, and I apologize for the fluctuations of my voice. I have a cold. There's some underlying themes in that vision that have to be brought out. One of them is the presumption that all those models integrate. And if you think about it, in a large system like an airplane, which is the typical vision of a digital twin, there will be thousands of models involved in that, from everything from CAD to ECAD to EDA to system models, et cetera, et cetera. If they don't talk to each other, you're not going to get to a digital twin. The other underlying presumption is that those models are credible. So just because you integrate them, just because you build them, doesn't mean they're right, or they're accurate, or they're reusable, or they're even interrelatable. So that's what we mean by when we talk about integration over independence. We want to get to that integrated model. Now, Phil Zimmerman suggests that model interoperability is a dead concept. I disagree with her. I think we can and must get there. Expressiveness with rigor over flexibility is a concept about the is trying to put a small r emphasis on the word rigor. So we're not trying to say you have to hammer down, thou shalt do system engineering model-based this way, because we want people to have the flexibility to build the models they need to define the systems they're building accurately. We also want them to be expressive in expressing those models and what's in them in whatever ways they need to express them to define that system. But what we're asking is that there be a little bit of rigor involved in it so that the models will interoperate. The models will be analyzable. The models will be credible. And then, of course, as I said before, we've encouraged people for 15 years now to build models, to create models, and I think we've done a good job of that. I think that the movement is moving along nicely. Now it's time to start using those models and think about not just creating those models, but creating them for the intent of being usable. And when and where do they become most usable? When they get reused, right? Copy is the most sincerest form of flattery. Sorry, I'm not used to speaking this direction. So I just covered that slide. We'll move on. The underlying principles to the value statements talk a little more in depth about what we mean by each of these. In this case, obviously, we're saying the stakeholder stands up front, right? And we want to put an emphasis on what we're saying here is that put an emphasis on just that, describing the information that you need for your system, not on the engineering processes. I had a 75-man engineering team one time, women too, and we were about a $500 million company, and I got accused of trying to make us a Hewlett-Packard. And I'm thinking, they're a $10 billion company. What's wrong with that picture? Why do engineers always want to rebuild the way they rebuild? So this talks about some of the independence. So feel free to use the formats, the structures, the language, whatever you want to be expressive in your model. But the underlying nature of system engineering models are semantic ontology. And if you don't know what a semantic ontology is, feel free to talk to me about it. I'd be happy to bend your ear. The importance of that is that it provides an essential key to model integration and model credibility. That's how we can, that's the underlying structure that if we can adhere to that, to some level of commonality there, we can then interoperate those models. What makes models difficult to integrate is that structure, is because it's a semantic structure. So when I say requirements bind components, that's a semantic triplet in an ontology. But what I'm not saying is, or what's missed, if all I do is capture that, is I'm not saying that requirements impose constraints, and constraints constrain properties, and properties, can't think of the relationship anymore. Properties apply to components, and if I don't have all three of those triplets involved in that, I don't know why I've bound that requirement to that component. And that's what's essential to get out. But if I do know that, and I can trace that, and I can put that in an ontology that is traceable and understandable by a computer, I can analyze that. Now I can analyze my model for hundreds of those kinds of things, and I can get to a model that might be accurate, that might be complete, that might be reusable, might be traceable, it might be many other things. This talks about the credibility, right? So unless those models are credible, when you get up to hundreds and thousands of models, you're either building something that's grossly not going to be cogent or copacetic, but it's potentially dangerous, especially in the world that I work in. In order to get to that, though, I would posture that if we could, instead of using humans to peer review a model, that if we could automate those models and automate the analysis of those models, we could build much more credible models. So in my space, I can think of a single model that has over 10,000 nodes in it. And I challenge anyone to think that a team of people, say 10 or 12 people working for a week, can cover that entire model and stand up and say, I certify it and think it's credible. What if instead I took 100 or 200 patterns and I analyzed that model against those patterns, 100,000 loops, and now said, well, I think that model is credible because those patterns are credible because those loops have gone through many iterations and variations and all kinds of things. Maybe now that model is more credible and useful. So this talks about how we might get there. A semantic ontology is a natural language process. A natural language process lends itself to augmented intelligence methods for analysis, even machine learning. When you get into models that are 10,000 nodes, that becomes a lot of data. When you get to 1,000 models that have that kind of data involved in it, you get to a lot of data, and you need to use something more than just a simple algorithm. But we think we can get there in that way. And the other half of this is that, don't forget the human. And the other part of that is that the reason to do that, the reason to build credible models, the reason to want to integrate those models is that we want to integrate all those models. We want system models to be integrated to mechanical models, to electrical models, to chip models, to everything else, and other system models too. My argument with the PLMs is that a PLM doesn't necessarily allow me to integrate between Magic Draw and Genesis, if you will, or vice versa. So we're looking to involve all of the engineers. And we would even contend that we need to start taking the system out of our name of MBSE, start calling it model-based engineering. Because we want all models to be integrated, all models to be working together. So that we can have cross-enterprise reuse of the CADs, the electricals, et cetera. We want models to be able to interlate. Back to the image again of the digital twin, how do we get there if those models aren't reusable, if those models aren't integratable and credible? And lastly, We asked the question over and over again, actually, why aren't we engineering our engineering system? Why don't we use systems engineering to create an engineering system that best represents how we should be building these systems so that we can be interoperable, so that we can be credible? We're in danger if we don't, if you think about it. And that's all I have. I have 2 minutes left. What do you want me to do with those 2 minutes?
Stand up and we'll keep doing what I have.
Okay. Thank you.